Assalamualaikum. My name is Saizari Zuhairi, and today I would like to present my research project entitled Preliminary Studies on the Effect of KOH concentrations on the physicochemical properties of OPKS biochar and OPKS activated carbon catalyst for trans-esterification of glycerol. To provide some background, biodiesel is a renewable fuel produced from vegetable oils or waste cooking oils. However, its production generates crude glycerol as a byproduct, which has limited industrial applications. With the increasing demand for biodiesel, the surplus of glycerol has become a significant issue. One solution is by converting glycerol into valuable chemicals such as glycerol carbonate, which has wide industrial uses. Based on the figure, there's a lot of methods available, but trans-esterification of glycerol with dimethyl carbonate is the most eco-friendly, offering mild reaction conditions and high GC yields. However, this reaction is slow and requires an efficient catalyst. Among types of catalysts, heterogeneous catalysts are preferred due to their ease of separation, thermal stability, and reusability. In this study, oil palm kernel shell or OPKS and abundant oil palm waste was chosen as a raw material to produce biochar and activated carbon catalyst. These two catalysts differ in surface area and porosity depending on their preparation. To enhance further their catalytic efficiency, the catalysts were chemically activated with different KOH concentrations to improve their surface area and porosity. This research addressed two key problems, which is the surplus of crude glycerol and the abundance of OPKS waste. It aims to turn these wastes into valuable catalysts and also valuable chemicals, promoting sustainability and also supporting greener industrial practices. The objective of this study are to investigate the effect of different KOH concentrations on the physicochemical properties of OPKS biochar and OPKS activated carbon, to characterize them using FTI art, SEM, Hammett indicators and TLC, and lastly to evaluate their efficiency in converting glycerol into glycerol carbonate. Next, I will briefly explain about my method. Firstly, raw OPKS BC and raw OPKS AC was obtained from MPOB. Then it was washed, dried, grind and sieved. Then it was treated or impregnated with different KOH concentration, which is 5%, 10%, 15% and 20%. And lastly, was calcined at 700 degrees for 3 hours. These catalysts were used in trans-esterification of glycerol with dimethyl carbonate to produce glycerol carbonates. The products, along with the catalysts before and after reactions, were characterized using FTI art, SEM, Hammett indicators and TLC. Next, I will continue presentations with results and discussions. The first result is FTI art spectra of OPKS biochar and OPKS activated carbon catalyst. So I will use figure 1F, which is raw OPKS biochar, have as an indicator to compare figure 1A until E, which is untreated and treated OPKS biochar catalyst. Firstly, OH vibrations peak at 3600 correspond to OH stretchings in alcohol or phenols appear in raw OPKS biochar spectra but disappeared in untreated and treated catalysts. Next, peak at 2300 could be related to the presence of COOH functional group also disappeared in figure 1A until E. This is due to high activation temperature in calcination process. It also stated that at high activation temperature, vibration at 1700 and 1300 for carbonyl and CO ether groups were destroyed, forming some polyaromatic structures. Researchers reported from pyrolysis in the presence of base destroyed the lignin structure containing the ester and ether linkage after the activations. In addition, disappearance of the functional groups at a higher temperature is an indication of hemicellulose and cellulose decompositions. Next, for OPKS activated carbon catalyst peak, it appear almost the same as OPKS biochar catalyst peak, but we just differ at intensity of carbonyl peak at 1700 indicate incomplete carbonization. Next, for FTI art spectra of pure glycerol, the important peak were at 3600 to 3200 vibration, indicating the 3 OH groups based on the structure of glycerol. Vibration at 3000 until 2800 indicate CH stretchings, and 1100 to 1000 indicate CC and CO peaks. Now I will compare the spectra of pure glycerol with the products obtained from trans-esterification of glycerol with dimethyl carbonate, supposedly GC, which use OPKS biochar and OPKS activated carbon catalyst. with different KOH concentrations treatment. So the most distinctive difference between them was the appearance of strong, sharp carbonyl peak around 1700, which correspond to carbonyl stretching of 5-membered cyclic carbonate of glycerol carbonate. Next is the band around 3300 indicates OH group was observed weaker and narrow compared to broad peak of 3-OH group of glycerol, indicate that the 3-OH group of glycerol were diminished and replaced by OH group of 2-hydroxyethyl chain of glycerol carbonate. Moreover, an additional COC peak around 1180 developed due to the cyclic carbonate ethyl linkage, and comparatively this peak was not observed in a glycerol peak. As you can see, 50% KOH treated OPKS biochar catalyst show that the most intense peak, GC peak around 1700 and 1180, show that this catalyst is the most efficient catalyst compared with other treatment. For OPKS activated carbon catalyst, most of the products, most of the key peaks of glycerol carbonate mentioned earlier obtained, but all the peaks were less intense than products of OPKS biochar catalyst. Therefore, treated OPKS biochar catalyst can be concluded as more efficient than OPKS activated carbon catalyst based on the conversion of glycerol to glycerol carbonate obtained in FTIR spectra. So now we will discuss about the next characterization, which is SEM-EDX. Let us focus on the OPKS biochar catalyst first. As shown in figure 9, untreated OPKS biochar calcined at 700 degrees for 3 hours develop greater pore volume compared to the raw catalyst due to the high temperature calcination, which promotes surface development and the formation of micropores. For treated OPKS biochar, as seen in figure 10, the pore size increased with higher KOH concentrations. However, if exceed the optimal concentration, it will lead to excessive carbon burn-off and destroying the carbon framework, which resulted in collapsing pore walls, which reduce the accessible surface area. This collapse of pore walls can be observed in SEM images of treated OPKS activated carbon catalyst in figure 12, where KOH infused into interconnected pore networks make pore less visible. The altered surface morphology explains the lower intensity of GC peaks in the FTIR spectra for OPKS activated carbon, indicating reduced catalytic efficiency for glycerol carbonate production. Next, the table of EDX show the domination of carbon in all catalysts. For treated catalysts, for both OPKS biochar and OPKS activated carbon catalysts, there were potassium percentage which come from KOH treatment, which decompose into potassium species such as potassium oxide that act as an active site, which contribute to the basicity of the catalyst, which will be characterized using Hammett indicators. So next, I will move on to the next characterization, which is Hammett indicator test. For Hammett indicator test, we want to study about the basicity of the catalyst. 3 indicators were used, which is phenolphthalein with a basicity of 9.3, 2,4-dinitroaniline with a basicity of 15.0, and 4-nitroaniline with a basicity of 18.4. After 2 hours, only phenolphthalein showed a color change, indicating that the basicity of the catalyst lies between 9.3 and 15.0. This confirms the moderate basicity of the KOH treated catalyst for both OPKS biochar and OPKS activated carbon catalyst. So the last characterization is TLC. So TLC was used to confirm the presence of glycerol carbonate in the products compared to pure glycerol. In the first trial for OPKS biochar catalyst products, the GC spot showed higher retention values from glycerol. However, dilation errors in the 50% KOH products led to poor separations. In the second trial, however, all products achieved higher retention values than glycerol, confirming successful conversion of glycerol into glycerol carbonate. In contrast, OPKS activated carbon products show poor separation between glycerol and the products, supporting the less intense glycerol carbonate peaks in the FTIR spectra and the collapse of the carbon structure observed in SEM images. In summary, 50% KOH treated catalyst for both OPKS biochar and OPKS activated carbon catalyst demonstrated the best catalytic performance as shown by intensity of key peaks of glycerol carbonates in the FTIR spectra. Characterizations provided key information on functional groups, surface area, pore volumes, basic strength, and product identification. While both catalysts effectively converted glycerol to glycerol carbonate, the 50% KOH treated OPKS biochar achieve the highest yield of glycerol carbonate compared to other treated catalysts. For recommendations, further characterization technique can be done, which can improve understanding of the treated OPKS catalyst. TGA or thermogravimetric analysis can provide insights into thermal stability of the catalyst. Brunel metallic or BET analysis can determine the specific surface area and micropore area. Proton NMR can accurately identify the compositions of the products, enabling more precise determination of glycerol carbonate yield. Lastly, the reusability of the catalyst can be evaluated to assess their stability and efficiency over multiple reaction cycles, which is critical for practical and sustainable applications. To conclude, further studies need to be done in order to gain more information and knowledge about the efficiency of OPKS as a catalyst in the trans-esterification of glycerol with dimethyl carbonate to produce glycerol carbonate. So I think that's all from me. Thank you for your attention.